Hello, I'm Professor Seth Chandler from the University of Houston Law Center, and this video is on decision trees and regression trees as part of the course Analytic Methods for Lawyers. Decision trees and regression trees are both powerful machine learning algorithms in their own right, but they also can serve as the building blocks for more complicated methods, such as random forests and various boosted algorithms. The main advantage, I would say, of decision trees and regression trees is that unlike many of the modern snazzy machine learning algorithms, they are interpretable. That is, they produce a method that a human being can understand. And so, while often they don't perform quite as well as advanced algorithms where every ounce of accuracy is important, such as, if you're trying to predict the stock market, or build an airplane or predict disease, but still they're important tools of machine learning. The other thing is that they're not as complicated as some of the other machine learning algorithms, and so therefore I think they're a little easier. Not only are they interpretable in their output, but they're also a little more fathomable in how they work. All right, here's the game plan for this video. First, we're going to take a look at the data that we're going to use. I'm going to come up with some measure of how well our algorithm is performing. I'm going to discuss the concept of recursion. I'm going to show you how to do a decision tree in Wolfram language, and then we're going to actually build a two-level regression tree and see how that works. All right. So, decision trees, you've actually probably been using them in various guessing games. Like I know with my kids, we had a game called Guess the Animal. And so, the first question you might ask is it a vertebrate? And they say yes. And then you say, is it a mammal? And if they say no, then you ask so I know that it's not a lion, a tiger, or a bear. And then I might ask, does it live on land? And when they say yes, I think, well, it might be a fish. And I say, is it a fish? And they say no, and it turns out that it's a mollusk of some sort. Anyway, but the notion is that you're adapting your questions to the sequence of answers that you got. And that, you need to have what's the next question regardless of what answer the player gives. Actually, it's really not that different from taking a deposition. If you think about it for lawyers, or interrogating a witness, which is you need to be adaptive. You might have some initial questions to ask, but then you need to follow up and narrow things down. And that's really the idea of a decision tree. So it's something that you're already familiar with. All right, so for the decision tree, we're going to work with the Fisher iris data that we've seen before that has, I don't know how many irises in it, and we're told they're the length of the sepal, the width of the sepal, the length of the petal, the width of the petal, and then we're going to try to predict the species of iris that it belongs to, Setosa, versicolor, or virginica. All right, that was easy. Let's talk about how we know if we succeed when we are doing a classification. So, first of all, let's just see what we have in our iris training data. And it turns out we have an equal number of Setosa, versicolor, and virginica irises. And so if we don't ask anything, if we don't play any game, you could guess any one of those. Ordinarily, with modal guessing, you would want to guess the iris that had the most. So if there were 38 versicolors and 32 Setosas and 35 virginicas, you're going to do best guessing versicolor. You're not going to do great, but it's better than guessing Setosa or virginica. So how do we actually write some code for modal guessing in Wolfram language? First, I'm not sure if we've seen normalize already, but the idea of normalize is you take some list and then you apply some function to the list. So here this would give us 12. And then you divide each element of the list by the function applied to the list. And so basically, this is just giving you, instead of 3, 4, 5, you're getting 3/12, 4/12, 5/12, which add up to 1. And so here's the code for modal guess. It just tells you, okay, pick the element in the list that has the highest value, and that's how it works. So supposing here were some possible distributions of irises that a classifier might come up with. Here's our original one. Here's one that looks more weighted towards setoses. Here's one where setoses and versicolors are in close competition. Here's one where we've just eliminated something. Here's one where it's real heavy for setosa, and here's one where we're certain it's a darn setosa iris. So there they are, and now let's figure out what the modal guess is for each of these and what the probability is we're going to get it right. So for this one, you take your pick, and you got a third chance of getting it right. For this one, you're going to pick 50, and you're going to have a 50% chance of getting it right. For this one, you're going to pick 49, and I think you see how modal guessing works. So modal guessing has the virtue of being, about as easy as it gets. The problem is that in multi-class settings, it doesn't do so well. So for example, it's going to think that this distribution here, 50, 25, 25, is better because there's a 50% chance of getting it right than this one, 49, 48, 3. And although 49 is less than 50, you've pretty much eliminated the third possibility here, and so many people might regard this as a better classification, a better separation than this, and modal guessing is not going to get you there. All right, Gini index, on the other hand, will. So the idea of Gini index is you take the sum of the squares of the probabilities, and then you subtract that from 1. So it's 1 minus the sum of the squares. If anyone's done antitrust law, it's related to the Herfindahl index, and you see lots of sum of squares measures in the world. In any event, here's the code for it. We're going to take a distribution that's going to be represented by a numeric vector. We're going to normalize that distribution so it sums to 1. We're going to run our famous power total function over that computes the sum of the squares, and then we're going to subtract that power total from 1. So if we were to map our Gini index over the test distributions that we came up earlier with, we could see, and a low value is good here, so we could see that, here we've got a 0, and we can also see that our 49, 48, 3 is doing better than our 50, 25, 25. And so the Gini index corresponds with certain intuitions as to what constitutes a good separation. Information entropy. All right, so we've seen various forms of entropy before, and you remember that for the discrete case, entropy is the sum of some products in which the first multiplicand is the probability, and the second multiplicand is the log of the probability, and then you have to take the negative of that. And the lower the entropy, it's like the Gini index, the lower the entropy, the purer the distribution. So it's not hard to program. The only trick is that if you do have things that are 0 probability, you've got to get rid of them because log of 0 is not well defined. Here's the code, the same functional form as before. I'll let you fiddle with remember we talked about logarithms with different bases. You take your distribution, you delete anything that has a 0, you normalize the distribution so it sums to 1, and then you run the p log p function on it using the dot product to implement the summation of products. So we can run our information entropy function over the test distributions. We just want to get numeric values. That's why the right composition with n is there. And so what we see is, again, if you get it all right, or all separated, you get a 0. Here we have a very low information entropy. And once again, our information entropy associated with 49, 48, 3 is lower than that associated with 50, 25, 25. This accords with the intuition of many folks. And so what you see is information entropy works quite similar to Gini index. They're not identical, but they're both alternative ways that work well of determining how well a classifier is performing. Time to talk recursion. All right, I'm going to tell you verbally how a decision tree works. You have some data, and you want to split the data based on its features. You can't use the class, the dependent variable, which is also known sometimes as the label, if you ever hear that term, because that's cheating. If you know the class, sort of your work is done, and you're not going to know the class when you confront new data in the real world. So you have to use the features, the independent variables, in order to accomplish the split. Now, there are a zillion ways you could split things, and you could also split things into multiple parts, but the tradition is for a binary split, to split it in two. All right, so you come up with some way of splitting the data in two, and you then look at one of your metrics beforehand on all the data, and you look at the metrics on each of the two splits with some way of combining the two resulting metrics, often just a weighted average. So maybe your information entropy was 0.7 before you did the split, and now the weighted information entropy is 0.5. And that's true if you split it in one way. Say, in our Fisher iris data, we split it on whether the petal length is greater than 3. Okay? But you could try another split. You could say, you know what, I'm not going to use petal length, I'm going to use sepal width, whatever. And you're going to split it based on whether that's greater than or less than 4. And when you do that, the resulting information entropy is 0.2. So that's a better splitting method than using the prior one that was based on sepal length, width, whatever I said. All right, so the idea is that you split the data in the way that most reduces whatever your success metric is, be that information entropy, Gini index, doesn't matter that much. And you're greedy in general. You don't try to pick like the second best or the third best splitting thing. You pick the best. Okay, now is where we get to recursion. If you think about it, when we do that split, we have two data sets where before we had one. One in which the splitting condition is true, petal length greater than 3, and one in which it's false. But you could just treat each of these two sub-data sets, each of these little leaves, as a data set and run the splitting algorithm again on each sub-data set. So that maybe now the best splitting algorithm is whether the petal length is greater than 5. And on the other leaf, maybe it's whether the sepal length is greater than 3. And so now you have 4 data sets, and you can split those up, find the best split for each of those 4, and you keep going until you meet some stopping criteria. That stopping criteria might be your information entropy or your Gini index is low enough, or you're not gaining much anymore. You know, the information entropy's gone from 0.03 to 0.0298. Or you might just not have very many members in a leaf. You might have gotten it down to 2 members or something. Or you might have done, you know, it might be 4 splits since the root. And so there are a number of stopping criteria that can be used. That's sort of the art of coming up with a good practical algorithm. But that's all there is. That's it. That's the decision tree. And there are, as I'm mentioning, bells and whistles. Like you might want to, once you've done the decision tree, you might try to figure out, should I prune it back? But this is why people like decision trees, because they're pretty easy to explain. And then once you're done, you have a program that people can understand. If the sepal width is greater than 3, then ask whether the petal width is greater than 4, and if it is, then it's a setosa, and if it's not, it's a virginica, and then you go back on the other leg. So let's actually see how a decision tree is implemented in Wolfram language, and you're going to be very happy here. Oops, wrong expansion. There we go. All right, you ready? Here it is. Classify, iris training, method, decision tree. We're done. Okay? You want to see how it performed? Classifier measurements on using the classifier function on the test data. And as it happens, because actually it turns out that the Fisher iris data is very easy, the decision tree for modern methods, the decision tree works splendidly. So you can have some options to the decision tree method, and one that I want to discuss is called feature fraction, where each time you split, you might not make... Hang on, we got a siren here. And now we've got a helicopter. But in any event, each time you split, you might not want to have all of the features available to you for choice. You might actually restrict the features. And remember I told you that it was a greedy algorithm? Sometimes a little less greed in finding something that might not be optimal can end up working better. And so that's one of the ideas behind feature fraction. It also might make the code run faster because you're not looking at as many things each time. So I'll just show you how it works. All right, and let's see how we did. And as it turns out, using only half the features, it worked just as well. Now, in bigger data sets, you might not have quite the same performance. You might actually have better in some instances, and you might have worse, but your code's going to run faster. I showed you decision trees at a high level, where basically you just run classify. I now want to actually show you regression trees, and since Wolfram Language has not yet built that in as one of its methods, I'm going to show you how to build your own regression tree and get a little better sense how all of this recursion works. All right, to do this, we're going to use the Boston Holmes data set that we've seen before. One of the reasons I'm using it is that what you're trying to predict is continuous. It's the price of a home, which doesn't fall into discrete categories. Now, your success metric can't be modal guess or information entropy or Gini index, because the values for those homes are going to be all over the place. It's not like there are just a few categories. And so those metrics don't make sense. The metric that's probably most commonly used is to look at the sum of the squared residuals within the leaves of the decision tree. So what you want ultimately is if that sum of the squared residuals was 0, you would have a perfect predictor. So what you want to do is to try and successively make splits in your data, just as you did in regression tree, such that the sum of the squared residuals between your guess and reality is minimized after the split. I'm just going to read this. The idea of a regression tree is to group and then subgroup the data points based on certain criteria, and then to make the prediction the mean value of the data points of the independent variable, of the dependent variable in the data points in the resulting leaves, so that even though the actual values of the homes in a certain leaf of the tree differ, your prediction for homes that satisfy the chain of questions that got you to that leaf is the mean of the values in the training data's leaf. So hopefully that makes sense. Let's see it in action and maybe it'll be even clearer. All right, first we're going to just label some things. So we're going to call our dependent variable y, and you know the form of the Boston training data, I hope by now. Right, it's just a rule. The left-hand side of the rule are the features or the independent variables. The right-hand side is the dependent variable, the label, whatever you want to call it. All right, so we're going to get, we've got our y values, and now we want to make sure we can compute the mean of the y. So when we start off, we're going to predict that everything is the mean. It's not Lake Wobegon where everyone is above average. It's here where everything is average. So that's our first effort at machine learning. It's a terrible method, but it beats any other constant. Let's see what our residuals are right now before we do any splitting. And so we're playing with 29,132.6 as our squared residuals. Okay. Now, let's split the data on the basis of variable 8, which is the weighted mean of the distances to 5 Boston employment centers. And my test is going to be, is the value for your home greater than or less than, or actually it's greater than or less than or equal to the median of the whatever these distances are. Okay, so we're going to take the 8th column here of the features. Here's our features, here's our 8th column, and we'll compute the median of it, and it turns out that it's 3.2157, whatever on earth that is. Now for some code. And we're going to talk about the map-reduce operator. The idea of the map-reduce operator is it's sort of a form of grouping plus. So I think it's easiest to see by example. Here's our resource function. Here are the arguments to the function, and here's our data. And you can see it's AX, BB, etc. So what we're going to say is group it according to the first value of every item. So we're going to group it according to whether it's an A, a B, an A, or a B. So we're going to have separated into the A's and the B's. Then, the only thing I want you to keep, though, is the last item of the data. So keep the X together with the Q together with the Z, and the V together with the W. And then, for each group that you've created, take the mean. Okay, let's run that. All right, and you can see that the X, the Q, and the Z are grouped together. The X, the Q, and the Z, I guess it alphabetized them. And it's taking the mean of that by dividing it by 1/3, and the V and the W are together, and we're dividing that by 2. All right, so we're going to need our map-reduce operator, and now you know what it is. We're also going to want a little function that computes the sum of the squared residuals. So the idea is you have some data y, you compute its mean, you store that in mu, and then you take the power total of y minus u, y minus mu, the residuals. So we've got that function working for us. And now let's use those. So what we're going to do is we're going to take our Boston training data, we're going to group it based on whether the value of feature 8, that 1 is there, because remember, we're dealing with the left-hand side of each data element where the features are, but we only want the 8th feature, is greater than that median. Then we're only going to preserve the second part of the data, which is the dependent variable. And then, for each of the groupings of those dependent variables, we're going to compute the sum of the squared residuals. So let's see what our residuals are after the split. And for the homes which had that feature 8 above the median, it's 8,430. And for those whose feature 8 was less than or equal to the median, it's 19,508. And we can certainly total those up. And now we have our new residuals after our hypothetical split. And you'll notice that is not the same as the residuals that we computed originally. It's slightly less, and so we actually have accomplished something. Now you should know that not all splits will reduce the residuals. There are some splits that are really bad, and they will increase the sum of the squared residuals, but if you do it well, you're going to reduce it. So let's write a little function that automates this process. The idea is we have data, and then we have a list. The first item in the list is the column number, and the second item in the list is what value we're going to split it at. So we're going to say MapReduce operator of the feature. Is it greater than the split value? preserve only the dependent variable, the second part, and then take the sum of the squared residuals, apply that to the data, and then compute the total. So that's what our SSR is going to automate, and let's apply it. Let's just test to make sure it works. So we're going to take our Boston training data, and we're going to group it based on whether the value of feature 8 is greater than the median of feature 8, and thankfully we get the same answer. Okay. Now, let's ratchet it up. Actually, this is not true. Make things a little better. I think in some earlier draft it made things worse. So let's now find every possible split of a feature. And the way we're going to do that is you sort the values, you take groupings of 2, and then you have offsets of 1. So maybe, I don't know if we've seen partition. Here, let's do partition. So here's this. Let's expand that out. All right, so here's what you get. The 1 and the 2 together, the 2 and the 3 together, the 3 and the 4, etc. And if you think about it, if I take the mean of 1.5, well, now I've split the data here. If I take the mean of 2 and 3, that's 2.5, so I've split the data here, all the way up to here where the split would be 9.5. So this is one way of finding all the possible splitting points of data. So that's the code that does that. And now, all I have to do is map this function, SSR, use the Boston training data. It's always feature 8 for now, and just let the split vary. What can the split values be? They're all the possible splits. And then I'll do my usual through terse and get the length of the result. And there we go. So what we can see is that for each different splitting value, we get a different sum of squared residuals. We can now figure out which is the best by sorting this association on the basis of its value, and then just taking the first value, because that'll have the lowest sum of squared residuals. And so it turns out that for feature 8, splitting at a value of 1.8727 works best. It gives us a sum of squared residuals of 25,696. But we're not done, because that was just feature 8. We have all those other yummy features to look at. So we could split on feature 7 or feature 2. And so now what we want to write is something that, first of all, automates that process that we just went through of best split on a particular feature. This just combines all the code that we did. Let's make sure that it works. It does. And now, let's run it on every possible split. And if you think about it, this is just the number of columns in, I'm just picking the first row here, but it's the same for all the rows. So we're going to map our best split on feature function using the constant Boston training data, but letting the feature to be split on vary each time. And chunk. We're done, and now we can find the best of the best. So let's actually write that code, since it seems to have gone missing here. And, or maybe I wanted to do it through this code. All right. So this is sort of a mess, but let's just eyeball it for a second. Feature 3 is promising. Feature 6 is in the lead. So it looks to, feature 13 in the end wins. No, I'm sorry, no it doesn't. Feature 6 still wins. Okay. Here's some code that does that. I don't think you need to understand that code. And it tells us that feature 6 is the best, split it at 6.978, and the sum of the squared residuals when you do that is 15,137. So feature 6 is nitrous oxide concentration. Not what I would have expected, but whatever. And now I want to turn this into a function. Let me just run this code. And so now we have our splitting function. Is the value of feature 6 greater than 6.978? And so now what we can do is have a function, optimal split, that just takes the data and then it figures out what is it figures out the best split on every feature. Then it figures out which feature is best, takes the first of that, and then it forms a function out of it in code that I don't feel this code you need to understand. That is, if you can get to here and understand what's going on in the code, I would count that as victory. All right, so that's our code, and let's just make sure that it works. And it does take a while, because think about how many different splits it's checking. Great, it works. So now all we have to do to get our 2 leaves is to take the Boston training data and split it according to this splitting function that we computed here. So, is this going to work? Let's see. Yes, it works. Okay. And so here's where the here are the homes where the nitrous oxide concentration is not satisfying this, that is, it's less than or equal to this amount. And here, although it's elided, are all the homes in which the nitrous oxide concentration is greater than 6.978. And by doing this, you realize we have actually cut our sum of squared residuals almost in half. So we've done a good job in figuring out home prices by just knowing the nitrous oxide concentration. Who would have thought? All right, and we can automate this whole darn thing in this code here. So this is going to give us the same result as we just got, but it's automated. Okay. So now, we have ended up with 2 leaves, right? The leaf where this thing with the nitrous oxide was false, and the leaf where this thing with the nitrous oxide was true. We also now need, though, to figure out if this is our model. Supposing we were to stop here, and this was our model, what would our model predict for future homes? And I believe I told you that the way regression trees work is it just takes the mean value of the dependent variable in each leaf. And that's exactly what this little code here is doing. And so it is saying, hey, if your nitrous oxide is below 6 point whatever, then your home is worth 20.0, and if it's higher, it's worth 38.1, which suggests that nitrous oxide is a good thing, which it probably isn't, but maybe being close to the city center where there's more nitrous oxide has compensating advantages. Anyway, I don't really care why this is happening. I just want you to understand how this is all working. And so now what we could do is we could see how to actually take this. Supposing this is our home here. We've got a home. Here are the values. We're going to compute how is it higher than is the optimal split function applied to this data true or false, and then we will look up in this association the value for this key. That is, this is going to produce a key, or it's going to produce true. So that's now a key that gets fed in here. Nested lookup is just a way of sort of sequentially descending through nested associations. And so we learned that this home would be worth 38.158. We have now succeeded in building a regression stump, a tree in which only one level of split is applied. But as I mentioned before, we don't have to stop here. We can now split each of our leaves in 2 so that instead of having 2 leaves, we will have 4. The good news is the hard work's done. Because really now all we got to do is to map our optimal split function over each of the leaves. The Boston training subdata is this data structure with 2 leaves, and what we're going to do is figure out what's the optimal split for each leaf. And so this will take a moment because it's got to figure out what all of the possible splits are for each leaf. But at the end, we find out that if the nitrous oxide was not high, then what we now want to do is split on feature 13 and find out if that's greater than 14.3. What is feature 13? Feature 13 is the rabble, the lower status of the population. So an ugly truth about home prices is revealed. All right. We are here in our efforts. And if the nitrous oxide was high, we're going to split again on nitrous oxide. Who would have thought that nitrous oxide concentration was the key to house price values? I might have to rewrite this because it looks like this time I must have run it on some other data beforehand when I wrote that text. I will clean that up before this notebook is published. All right, now let's do the split so that we end up with 4 leaves. And here, this might be the little most complicated piece of code. I think we have seen merge before, but let's actually make sure that we understand it. So I'm going to show you an example from the documentation here. So we've got multiple associations, and what we're going to do is we're going to first group everything with an A. So A now has 1 and 5 with it, and B now has 2 and 10 with it. And then for each of the little key value pairs, we're going to take the total of the values. So the 1 and 5 turn out to be a 6, and the 2 and 10 turn out to be a 12. For little Mathematica, Wolfram language nerds, merge is kind of like map thread for associations. All right. So here what we're doing is we're saying, well, we've got one thing, which is the training subdata, which has false and true as its keys, referring on whether the nitrous oxide thing is high or low. And now we've got another association, which is the new test to be run. And what we're going to do for each of the data splitting pairs is to group the data, the first thing, according to the application of the second thing to the independent variables in the data row, in the data. That is, first is going to give us the left-hand side of that rule. And so that is what this magical code is doing here. And terse 10 didn't do a lot for us. Let's just take that out for the moment. And okay, so now you can see what's happened. Here's the data. Here are the homes for which the first test on nitrous oxide was false. And the second test, which has to do with the rabble, was here. And so those have fallen here. Evidently, there are quite a few of them. Come on. Ah, here we go. Now, here's the data for which the first test on nitrous oxide was false, but the second test was true. And if I go down yet further, now I have the outer key again of true. So these are the homes for which the first test on nitrous oxide was high, but there's a low fraction of the rabble. And I'm not going to go through the fourth test case. All right? So that's our data structure. And I want to see if I can't get that. I don't know why that my terse didn't work. Terse. Maybe we'll try 15. There we go. Much better. Okay. Now, we're just going to automate it all. I just write a function that basically encapsulates everything I just did. So it takes the training data, it produces a first level split here. Now we compute the second level splitting functions, and now we compute the second level splits. So if we run that, I guess let's verify that that works. Regression tree of Boston training. And let's terse 15 that. And not putting the 2 slashes twice. All right, this might take like 10 seconds. 8, 7, 6, 5, 4, 3, beat me. All right, and I hope we get the same answer as we did before. Let's just see this 0.26. Yay, we get the same answer. All right, so it works. We're not quite done because remember, not only do we want the tree, but we want a function that predicts. So what we then have to do is to go to every leaf of the tree and find out the mean of the dependent variable of part 2. I'm mapping it at level 2 because we have a nested association. We have an association of associations, so I have to go deeper into the data structure to do that. If I do this, it's going to take a moment because it's actually recomputing that whole tree thing. But we now say, okay, here's our predictor. If the nitrous oxide is low and there are few rabble, then it's 23.4. If the nitrous oxide is low and there are lots of rabble, then it's 15.0. If the nitrous oxide is high, then if there are, what is this? This is low rabble? False is, this is interesting. It goes the opposite way. Low rabble, 32.4. High rabble, 45.4. So it's a little odd. I would want to really look into what's going on here, but I'm pretty confident the code is in fact correct. And this is, I've given you an idea of how these regression trees work. So the final piece of the puzzle we need is to actually come up with a predictor function that will work on new data. And this is that nested lookup thing I told you about. So we can now, we've generated a function, regression tree predictor function, which is ultimately going to give us a function that we can easily apply to new data. So let's just run it, and we're going to see, here's our function. That's it, and you can see here are the tests built in. Here's sort of what the right answers could be, and we can map this function over test data that we've never seen before, and it's able to make predictions. What we can also do now is to compute the sum of the squared residuals on our training data using our 2-level regression tree. We can add, that's for every leaf. Those are the 4 leaves. Add up the leaves. And now what we can do is to compare the sum of squared residuals on our new, right, we can get the sum of the squared residuals using our 2-level regression tree here, where we're going to map this predictor function that we built right up here over the training data, and then for each one of those subtract the actual value. So this is computing the residuals. I'm sorry, this is computing our predicted value. This is the actual value, so the difference is the residuals, and we're going to take the sum of the squared of the residuals. That's what we get. And we can actually now compute the R squared, which you can do using a rescaling operation, where the idea is to compare where between 1 and 0 the sum of your squared residuals now lies versus where it lay when you basically had no model and just predicted the mean. And we get 0.72 as our R squared, which is certainly respectable. Let's compare that to what we would get if we ran some snazzy thing without all of my decision tree, regression tree things. It seemed to have picked gradient boosted trees, which we will talk about in the next video. We'll talk about boosting. And let's see how the snazzy gradient boosted trees, which by the way is a pretty state-of-the-art algorithm and like wins competitions, let's see how it does. And it did get 95% right, so we're feeling our algorithm's a little shabby. But let's see how we do on the test data, because after all, that's what really matters. And our algorithm, our two-level regression tree, gets a 0.625 on the test data. And let's see how our gradient-boosted trees do. It gets a 0.81. So we have still lost with our two-level regression tree, but it's not terrible and it's not degrading a huge amount relative to our performance on the training data. So we have a method that's explicable. That is, I can say, here's how we figured out what your home was worth. We found out that these sequence of questions did the best job of any really sequence we could find in figuring out the home value. Here's what we ask. We ask about the nitrous oxide concentration, and we ask about the rabble in the neighborhood. And that's how we came up with your home value. I suspect Zillow does a better job. All right, so that's it. Decision trees and regression trees are useful. They're interpretable. They're simple, so they tend to be low variance. That is, they won't degrade that much when it sees test data. One of the reasons I'm spending time on these algorithms, though, is not just because they're interpretable, but because they're also the foundation for two other methods we're going to see. Boosting tends to work with regression trees, and random forests tends to work with decision trees, although both of these can do the other thing. That is, they can work with regression trees or decision trees as well. Thanks.